It's a pleasure to be here. I have to tell you quite frankly, I looked up on UwTV and all the famous people that came to speak, and I'm like, why did they invite me here? But I hope you'll at least like the premise of the talk, the title of the talk, and there's some great things afoot. No disclaimers to make this afternoon, but the claim I'd like to propose and today's topic is with all the wonderful developments in sequencing and DNA technology, there's maybe a 1 or 2, sometimes a 3-decade lag in laboratory systems and hospital systems for electronic ordering and reporting and often interpretation. And the full potential of these DNA technologies cannot be reached until we have parallel advancements in that same laboratory information systems and hospital systems, electronic health records. So that's the claim for today's talk. Just a word or two about ARUP Laboratories. Many of you are familiar with them. Nonprofit enterprise owned by the University of Utah. Started back in, I think, maybe 1983. Owned by the Department of Pathology, operated by faculty and medical directors there. One of the nation's leading reference laboratories, clinical and anatomic pathology, and currently at about 3,000 tests and test combinations and somewhere north of 40,000 samples a day coming through the door. About 10% of those are molecular, is the slice of that part of the business. And clients from across the country, different states, a lot of the academic and teaching hospitals and children's hospitals, government and military contracts and so forth. My role there, specifically the last 2 or 3 years, as next generation sequencing panels and assays have launched, my role has been to put computational infrastructure, hardware and storage in place, and also staffing in place to support those assays launching. So this afternoon I'd like to cover 4 areas, kind of roadmap out this idea of clinical reporting, including some of the challenges, opportunities there in the reporting arena, staffing and expertise, capturing structured data, and summarizing the supporting evidence that surrounds a variant once it's found. So I want to think for a moment, those of you that spent a lot of years with a pipette in your hand or on the bench, you think of your little slice of work, you get the samples in, you do the capture or library preps, those types of things, you get it on the instrument and run it. Some pipeline ensues, you've cleaned up the data, you've made a list, and you throw up your hands and shout, hooray, I'm done. And you're excited and the next batch of sample comes along. But we want to take a step back and see in the context of laboratory medicine, there's a lot of traditional platforms and instrumentation that laboratories use. Next generation sequencing is just one of many. It must fit within the healthcare system as it is currently today, including physician order entry, electronic orders, clinical reports going out. There's also things like incidental findings or if a variant's reclassified. It has to fit within that workflow, including reimbursement, for that to move forward successfully. So in that regard, it may come to play a dominant role in laboratory medicine, but it certainly needs to fit within the context that's in place in healthcare. So where are we now? The great examples and some great examples here as well in the lab medicine department. Not just DNA technologies, but a lot of other technologies as well, flow and mass spec, cytoarray, some things like this. Lower the cost and increase the speed of the analysis, and they yield much larger and larger data sets. So gene variation is currently being discovered at a very, very rapid pace. The challenge that presents then is this widening gap between what's discovered and any real widespread or practical implementation in a clinical setting. There, here and there across the country, there's great examples of that starting, but certainly not widespread in patient care today as it has potential to be. So we'll spend a few minutes, let's talk about some of the challenges specifically when dealing with next generation sequencing and reporting those results back to the ordering clinician. So this slide just simply serves as a reminder as you move from a single gene test to a panel, to an exome, and then to a genome, that there's a corresponding increase complexity in both in file size and analysis time as you lay families or pedigrees or trios on top of that, and across the population, certainly it also increases again in complexity. And this is a very different paradigm than traditional laboratory testing, where it's a single test order, a single value, here's the units, here's the reference interval, and all of the laboratory systems in place for the last couple of decades are geared towards that type of laboratory result. That is not the same as this type of information, where there's can be hundreds, thousands sometimes of results that you're looking through. Just a reminder of the FASTQ file format. Many of you might be familiar with this, some of you may not be, so just serve as again as a reminder. It's quickly becoming the de facto standard of the output of the instrument and also the input for any data analysis and pipelines. And you will see here the read name as assigned, the actual sequence read, an optional comment line, base quality scores, and ASCII code. But what I want to point out is this is kind of what the file looks like. If you're crazy enough to open it on your laptop, maybe a notepad or something, you'll have to page down like 10 million times to see the whole entire file. They're quite large and kind of an approximate size here on the bottom of the slide per exome or per genome. If it's paired end, you'd have 2 files, so they'll of course be larger. But that's the starting place in terms of pipeline or informatics, is the FASTQ file. I also want to mention just a brief comment about actually the computing environment. So many of the instrument platforms, including HiSeq, MySeq, and IonTorrent, Sequinome, some of the others, operate in a Linux environment. Much of the open source or academic groups and pipeline and software also function in that environment. File types and many of the annotators also function. So when you talk in terms of users and clinicians, or maybe even a patient view, largely based in Windows, browser-based, you want to expand into that user environment, complement some existing workflow that's in the laboratory. Whether you're going to view, you submit a job, where is it in the pipeline, is that job status, some quality metrics, results review during test sign out, or if a clinician or medical director wants to capture some notes or comments about that result, likely they'll be in a Windows environment. So many times what's the go-between is some type of an archive or some database that sits in between. And as you move to a browser environment, browser-based, that's a nice way to marry those two environments. But this is a very different skill set than, say, a med tech on the bench or a genetic counselor. For these steps to run very smoothly, obviously a very different skill set than some traditional hospital or lab medicine roles. Another topic that can be challenging during the data analysis steps, talk about benchmarking for a moment. This comes in 2 pieces. You'll want some standardized data sets. There's excellent work, a recent paper of ARUP, the HapMap and CAP, CDC and NIST, some of these ideas, genome in a bottle, where the point is it's a well-validated, controlled data set. You know the answers and know what you're looking for. The counterpart to that is in the pipeline itself, you'll want some automated fashion or module built within the software that allows you now to ask, is pipeline A better or is pipeline B better? But you can't do that step without the standardized data set as some ground truth or as a starting place to compare the benchmark and the engine and the metrics. This is not well done by too many groups, maybe 1 or 2 out there. But it's certainly an important component. The point there to the whole slide, until we arrive at the perfect algorithm at some future date for alignment, for variant calling, it's certainly an ongoing effort. And that is enhanced when you have a standardized data set that everyone can use and agree on. Downstream from that slightly is the topic of false positives. I spent 10 plus years working in proteomics and mass spec area, and early on, it's laughable now that you look at it in hindsight, but we were always curious, why do these top 1 or 2 or 3 things show up on all of our lists? and then you do another experiment a month later and you see kind of the same 2 or 3 things. So now you think in terms of, is it technical noise? Is there some issues with reproducibility? Did I forget to wear gloves when I did my sample prep? Cytokeratins or something else showing up. There's a lot of analogy to that in next generation sequencing. So what we tried to put in place internally, we have data scientists or the disease scientists themselves will sit down and look at the data in a given viewer. IGV is the one that we use the most. We try to capture their thought process as they look and they evaluate the screen and say, is this variant real, or do I trust it or not trust it? And we try to capture that same thought process and automate those steps in a computational fashion. So this relies on likelihood, some quality likelihood scores divided by depth, and we take frequency counts on the y-axis. So what we're looking for is simply, as the scientist sees in the viewer, one that they think is real, and one that they know is probably not real, that's false. We then use a strategy of binning and this quality score and the spread or the delta between those bins that we can, in essence, remove everything that they would remove by hand, we can now do in automated fashion. The advantage of this is if you don't take these out at this point, downstream, these will come back to haunt you at every single step during interpretation and reporting, because now you're not sure, have I dealt sufficiently with false positives or not? And again, along with benchmarking and other issues, an important challenge in reporting. Scientists love spreadsheets. I'm sure everybody is quite familiar with Excel. The point here is with a simple panel in a working environment, we're dealing with about 200 to 300 lines or entries. For a simple gene panel will be upwards of 30,000 in an exome and 3 million, 3.5 million in a genome. And I don't know about you, but my brain quickly turns to mush when I try to focus on 8 or 10 things at the same time, let alone like 30,000. So we need better ways to sort through the information, more automated, more robust, in terms of quality control, in terms of annotation, in terms of reporting. Although spreadsheets are a great research tool and to send results back and forth to one another, we can probably do better that in a reporting environment or hospital system. That simply gives you an idea of the amount of results in a given gene panel or clinical exome. Leads us to the next topic. I want to talk for just a moment about staffing and about expertise. So it shouldn't surprise any of us. Many of you caught the news yesterday about the BRCA testing. Angelina Jolie, that was in the news yesterday. Prior to that, there's a lot of things about de-identification of sample or re-identification of samples in this type of data. The point here for today, many people are beginning to realize it actually costs more to analyze the information than it does to generate in the first place. And for those in this room, that may not be a surprise. It's not even specific to DNA sequencing. A lot of instrument platforms are that way now. So when I think in terms of a bioinformatics or data scientists, we want to split this process into two. One is the step where the samples are prepped and they're on the instrument, the raw reads are coming off, and someone needs to take now the sequence reads and get them cleaned up, get them prepared to do the next step. So we're thinking in terms of alignment, of variant calling, false positive removal, those types of steps is what I'm considering here. Also a term maybe SQL or archive things. And that really belongs in a computational environment more akin to computational biology or an IT and database environment, programmer environment. The other half of that, and the important counterpart in a lab setting, now we're thinking in terms of medical geneticist or counselor, where they actually have to sit down now and start making some decisions and some choices. And that's really an interpretation step where can the data be trusted? Was it a good, clean run? Is the variant real? Has it been seen before? What does it mean? What should we do about it? So in our workflow, in our process, we've really kind of think about those two things separately, although it's certainly a spectrum and a continuum there. One more point there to mention. again, each slice of the work, each group might celebrate, they think they're finished, but actually there's always one more step to be done downstream of that. And the point there is, as you move from data towards knowledge, follows this continuum of the required skill set. So this is kind of, at least the skill set should include this for start to finish for a team. You're thinking in terms of disease and data scientists, you're thinking in terms of some bioinformatics support and programmers, systems admins, database design and admin, user interface and some web design work, annotation sources and keep those up to date and as that's curated. A very important piece that's often neglected or wait till the very last is lab interfacing and standards type work. How does it interface with enterprise warehouse or a clinical data repository? And of course, the medical geneticists or genetic counselors come into play towards the end of that process. But again, the point to move from raw sequence reads towards actionable knowledge and interpretation and therapy for the patient. But a wide range of skill sets and software and hardware. So in order to keep the presentation pretty vendor neutral, I just want to point out there's some great, not only academic groups, but there's some great industry efforts in these areas, pipelines, data archives, annotation sources, reporting, interpretation, and interfacing. The standards even has some great efforts. And I'm happy to visit after the talk about specifics. But the point there is, for an academic group, as I'll mention later, to start from scratch is not always the best strategy if there's some expertise or head start that you can leverage, whether with another academic group or within industry. It can give you a great head start. Start to finish, I don't know of any one company that does all the steps well. So you'll end up chaining some pieces together at some point. But there's some great success across industry and some great efforts out there. That often leads to the question about, in traditional, in a hospital or other industry setting, should we build it ourselves or should we try to buy some pieces? The things we think about here are one size doesn't always fit everybody. What we really need might not even exist out there in industry. And no matter the industry or the instrument platform, there's always a bit of a lag time, maybe perhaps a year or two, between the actual software and the release of the instrument. So the software lags behind, usually months to a year. It's a rapidly changing field. Many startups and groups are vying for that same market space. In the near term, some of that field's a little unstable as maybe one company is out of business, another company buys another one, and clearly it's not free that you pay for that product and that expertise. On the other hand, if you choose to do it internally, you might think, well, this will protect us from maybe a merger or going out of business or some acquisition. We can customize it to our own workflow, but it requires a lot of dedicated expertise across several different these areas. But you can leverage internal people and resources and put those into play. But of course, again, it's not free. So you sit down and list all the pros and the cons and the pricing, and you come up with your best strategy about what pieces you can do internally versus what you can outsource or what you can buy commercially. And that's a great exercise to go through if you've not done that before. One last note about that software environment. Many of us are familiar with that research or that academic setting, open source setting. That's very great. It's fluid, it's dynamic, it's very collaborative back and forth. That environment is not typically not adequate for CLIA accreditation or FDA medical device, for example, where you're thinking in terms now of industry standards of coding, code and commenting your code, CAP inspections or documentation, software control, version control, and software quality. If you want to leverage an existing service object architecture like role-based logins, if that piece is already at play within your institution, you shouldn't have to rebuild that. You simply use that module. So there's some things like that. In a production setting, software maintenance and help desk and support, this environment is very different than a research environment. And I simply want to point that out. We'll talk for just a moment about structured data capture. The main point here for this section is that structured capture of data is really the key to flexible reporting. You might want to think in terms of having a separate space, a data mart or data cube warehouse will likely be needed, separate from the research setting. You might want to think in terms of a staging area. So it's kind of an in-between where the clinical samples on hold as you're sorting through the data and the results and the reports before the final report is released. And in our hands, at least, we've been somewhere between maybe 40 to 80 terabytes of storage space as you consider the staging area and you ramp up panels and more samples start to come in over the months. That's kind of a comfortable amount that we've found, which may or may not be available in your institution or on campus, or it can certainly be purchased. The point again there is to capture the data how you need it is really the key to flexible reporting. A nice starting place that many of you might be aware of is NCBI has recently launched a genetic testing registry. This GTR gives a list on their submission template of a minimum set of fields that you'll want to capture about as an assay launches. You'll want to capture a lot of this information. There'll be a few things specific to your institution or internally to capture as well. But these are some key fields that as you look to export data or share data across institutions or across with collaborators, that at least now you have some common data elements and data fields in place that you can begin to share with others. What that might look like internally then is you have things you can filter on. You have lists of annotation, CDOT or PDOT numbers, population frequency. There's another 10 or 15 columns that you can add as you need to. You can pull in phenotype information. You can pull inheritance patterns, human gene, the mutation database, and maybe a gene summary. All those things captured independently can be now very flexible, put into any type of a viewer or report to use internally, regardless of who the audience is. Unfortunately, some of the historical constraints to a laboratory system and the way that reporting is done in electronic reporting. I was talking with my boys the other day and they had never watched TV on a black and white TV. And I'm not even that old, but I've at least seen a black and white TV. An 8-track tape, they don't even know what a cassette is. And we have a few CDs around our house. And for sure they don't know what a fax machine is. So in reality, if you can't browse it or tweet it or text it, in today's world, you might be behind the curve a little. So in terms now, we're thinking in 2013, we want to report this type of information, but maybe our laboratory system is stuck back in the mid-1980s. And that's the reality of what we need to work around and understand those limitations, those opportunities. One other thing I want to mention there, when we think in terms of a gene test and report, we're thinking now in terms of strength of evidence as we move across the spectrum for does it cause disease. Out in the middle, a kind of a gray area, we're not real sure what this change does, versus all the way over to it's causative, it's pathogenic, and for sure it's associated with that disease, it tracks in a family, etc. The irony of the situation, and these categories were recommended in 2008 by ACMG, and they're for the most part widely accepted. In literature and in clinical settings to this day, we'll still see different versions of this, such as it's benign, or it calls a polymorphism, or it's a SNP, or it's non-causative. People still use terms like unknown or uncertain, or variant of uncertain significance, or it's indeterminate. They'll still call it pathogenic, or it's deleterious, or it's causative. They'll throw in a few qualifiers like mild or severe. And then in an effort to make it more clear to a patient or a result, they'll toss in some qualifiers like likely, or suspected, or probable. So by the time you do the math, this is like 70 different combinations of a result that could go out. And so we think in terms of standardizing report and using a standard vocabulary, a standard term. There's, again, some opportunities there. The last section I want to mention is once your data is cleaned up, you've done benchmarking, you've removed false positives, etc. You've found a few things you're interested in. Now, in terms of summarizing everything that's known about those variants and how to go about that in a reasonable manner. So when I was a young kid in Arizona, I grew up in southern Arizona, I spent a lot of time in the cotton fields. So in the summer, they have kids chop cotton And it's not actually chopping the cotton plant, it's chopping the weeds that grow in between the cotton rows. But the phrase there, the analogy is, as the canal fills up and the ditch fills up and they start the irrigation, they want the water to get all the way to the end of the field. And if there's a gopher hole or the row's full of weeds, the water will not get all the way down to the row. So in my work, I like to not start with the instrument. I like to start with a final report all the way at the end, and I like to work backwards towards the data. And hopefully I meet somewhere in the middle with the information coming the other direction. So I think in terms of an integrated report, you brainstorm and think of your perfect report as you're in a clinical setting and you're dealing with patients, what needs to be there right in front of me at that time. And you might think in terms, depending if you're heme path or flow or fish or informatically inclined, what does the patient have? How much disease? What is the disease burden is there? What drugs will help? Who needs the treatment? Who qualifies for the treatment? Who's going to pay for the treatment? Sometimes the reimbursement comes into play. What is the dosing? So we're thinking now in terms of real time, on demand, right in front of you, everything that you want to know at that setting, at that moment. And that's really the goal of personalized care, personalized medicine, and great patient treatment. The question I spend a lot of time thinking about, how do I leverage and how can we leverage existing gene variant information? How do we leverage that best for clinical use? So in terms of what was found and what does it mean and what to do about it, if you're clever this afternoon, you'll notice those are weighted for importance. If any of you are old enough to remember Fat Albert, right? This is especially true for variants of uncertain significance. When it's novel or nothing else is known about it, how do you summarize the evidence around that? And do you trust a clinical or a predictor, some in silico tool as such as a predictor? So this is the question I spend quite a bit of time thinking about. I'm going to mention 4 quick areas within summarizing this evidence. We're going to think about ranking functional damage and gene relevance to a given disease or a panel. Talk for a moment about annotation sources and classification of a variant. And then I'll give a couple examples of recent work that deal with multiple predictors or integrating both phenotype and indicators with molecular information called integrated evaluation. So we built a great tool internally, VAR Ranker we call it, and now we're thinking, in terms we find something on our list that appears to be quite damaging, but it has nothing to do with the question that we're asking. It's not in the pathway. It has nothing to do with the biology of what's wrong in the person. As opposed to, it's pretty interesting. It's maybe in a related pathway, but it's way out in an intron and nothing changes in functionality. So really, we want to focus up in this quadrant where it's known to cause a change, whether structural in a protein or function or binding, and it's in a relevant gene and or pathway. So really that's where we want to focus and let the cream rise to the top, so to speak. In terms of once the variant's found and you've filtered out the ones that you're most interested in, we want to pull from sources of annotation, everything that we know about that, where it's been published, what groups have worked on it. So there's a lot, and I've not so much focused on commercial entities as I've focused on the actual raw source of the information itself and the annotation source. And both in cancer and other genome work, there's great resources out there. Some are more public, some are more private. The point here is even very high quality data off the instrument isn't really worth very much without an annotation that you can trust. So large amounts of time and effort go into that process. And if you're starting from scratch, it's probably not best to do that alone. This is an example, a great example where it might make sense to leverage some head start with an academic or industry partner. The notion there of you get what you pay for. Some of the public sources are great and they're free and they're easy to get to and they're widely available. But to use that in a diagnostic setting, If it's my daughter or son or a grandmother or something, I'm not sure I want her treatment based on what somebody uploaded to NCBI or DBSNP, for example. And if it was myself, I know I wouldn't want that. So it comes down to this idea of trust. I nearly flunked my PhD work because I used the word trust, and they said, well, what does that mean? And I said, I don't know, but when I see it, I know it. I know if I trust it or I don't trust it. And I had to change the wording around before they give me their signatures. In terms of classification, we're thinking now, different from annotation, we're thinking in terms now, a decision's been made, the evidence has been evaluated, someone's signed it out, and they've given it a category, and it's now this. It's either pathogenic or whatever it is. So in terms of classification, that's what we mean. Again, some great effort. Groups across the country have worked on this, and has been seen before. What was it classified? Has the classification changed across time because additional evidence has come out? And similar to before, even with high quality data and great annotation, if you don't have a classification that you can trust, again, you're kind of stuck and you're not sure what to do as to move forward. What we found here, there's a lot of big advantage to capturing both the clinical and research variants in the environment of interpretation. And even more so if you can share across the national level. There's great progress being made on that front as well. But another example of where you might want to leverage an industry partner or academic partner that has a little bit of a head start in this area. But again, it comes down to what group looked at the evidence, who signed it out, which groups do I trust more than others, or did I go to school with that person, do I know them, whatever, who can I trust, and where did that classification come from? Is an important question and a fair question to ask. In terms of, I mentioned integrated evaluation. This is some great work published recently from Spurtle and Thompson and Goldgar, Taftajian. Their work is multifactorial and likelihood of models. So in essence, what they're trying to do is combine multiple predictors combined with phenotype and indicators to increase or improve the accuracy when you evaluate an uncertain variant. So they focus on very specific things like breast cancer or mismatch repair genes. But the point there is they very systematically work through this list of changes in the gene, and in a statistically sound manner, they apply the exact same function and model to everything, score it, and see, here's my known benigns, here's my known pathogenics. Here in the middle, everything that's uncertain, let's score them exactly the same way and see, do they look more like the ones that are pathogenic, or do they look like the ones that are more benign? So there's some very promising work on that front. Closer to my own work that I've worked on the last year or two, when I think in terms of laboratory medicine, and I think in terms of traditional laboratory reporting, a very established report is here's the result, here's compared to a range or some population range, and it gets a little flag. Is it abnormal? Is it high? Is it low? Is it fit within the normal reference range? So in a gene-specific setting where the disease or the gene is well studied and well understood, there's a lot of information that we can leverage there. And for example, this is in thyroid cancer and the RET kinase. If you apply the same predictors across all the benigns and you do the same steps for all the pathogenic, they'll come out to a certain score framework or a scoring framework or metric. Now if I take all the unknowns, everything that's uncertain, and I apply the exact same steps, they now begin to cluster at either edge. What's interesting is that it just makes maybe a reporting or a metric that is clearly understood by a clinician, because now they think in terms of a reference interval. And we report everything else in laboratory medicine that way. I would argue probably gene test results can be reported in a similar manner. People will claim, well, this only works for things that are well understood, that you know a lot about. But if you put the framework in place and you move across the weeks and months, if you launch a panel and you see more and more variants across time, you'll certainly you'll see a lot more variants. And across time, we'll know more and more about those, that disease setting or that panel and those results. So it's a great framework for that. Just a word about target audience templates. So in every high school public speaking class or college class, they'll tell you to target your audience, right? That's one of the things that you learn in public speaking. So we want to think in terms now of capturing pretest information, and we want to think about drafting templated wording, and maybe a different view. It's a very different technical view versus a patient view. It might be a very different view of the information, and how to deal with that within the existing hospital or laboratory environments. So this is our PDF for Outport for collagen 4A5 for collagen testing, and it's a PDF to be downloaded, or they put it with a test requisition. It can come in with a sample, but if it's not filled out, a genetic counselor will have to call or fax it to somebody. They'll have to fax it back, all those types of things. So there's great opportunity there for a web-based form, or to make it part of the order entry itself as the physician orders the test. But again, when you think of terms of 8-track tapes and fax machines, that's a long time ago. Why are we still doing this? Many physicians would argue, well, I don't want to spend the extra 2 or 3 minutes to fill something out like that. But this is not a $6 little chemistry test. This might be a panel, or it might belong to an exome that's several $1,000s. And a couple extra minutes for a test that costs several $1,000s might certainly be worth the time. The point there is interpretation cannot be done very well in a vacuum. So if the clinical details come across with the sample, and the interpretation is done with all the information up front, it's better for everybody. It's better for the geneticist, it's better for the patient, and we have a better interpretation at the end of the day. A recent trip to St. Louis taught me an interesting lesson. To draft wording is actually, seems to me, one of the very most laborious time. It's just hard. So they started with about a nice half a page, and the oncologist said, that's way too long. So they got to a little short paragraph, and then they said, oh, that's still way too long. We want one sentence, very clear, very concise. So the goal there is to take everything that's known about what you just found and distill all of that into a very clear sentence of what it means, what was found, what it means, what to do about it, right? And nobody wants to spend time reading a big page full of details. So with this process in place, and it takes a lot of time and effort, you get to the point where you simply have a very nice, clear sentence. If that has been seen before, use the exact same template in the wording. If it's something new, it might come up, the fellows might be helping, or you might meet every Friday, whatever the case would be. But to have a process in place during sign-out that you can draft out this wording, make it very clear and very concise, and that is prepared ahead of time, and the draft template simply is pulled up and the sign-out goes forward very smoothly. And again, it might seem like it's a lot of extra work and just ignore it, but over time, as you put this into place, the process will get more and more smooth as you see more and more variants. The point here to this slide, as you capture structured data, once captured, you can put it in any format that you want it and customize it to the customer, so to speak. It pulls from the same core data set. So in this view, you might have a very technical view, maybe for a genetic counselor, a lot of links that they want to see, all pulling from the core set of data. In terms of maybe what a treating physician want to see is more in terms of management or treatment or prevention, surveillance, can pull from the same core set, but now you have a very different view depending on who's looking at the data. And across the top, just a very, very short summary of actually the finding. Talk for a moment about limitations of current interfacing and electronic reports. So we covered this a little bit already. When you have very discrete fields and you display it how you want versus sending out 4 or 5 pages of a fax text, one big blob of text, what we need to do a better job of is internally capturing the data, figuring out the best way to interface into systems, or if it's an old legacy Cerner or Epic system, maybe how to bypass that or get around that and augment that system in that report. This is not easily done because it involves warehouse groups, interfacing groups, HL7 groups, orders and reports. And but it's in a certain an important part, certainly. The point I want to make there, I think that's key, I alluded to earlier, is across this same period of time, we've seen very, very rapid advancements in DNA sequencing, both in terms of turnaround time and labor and cost, where an example laboratory here might have kind of a local system. Their interface local means that they print something out and give it to somebody or fax it. You might have picked up Cerner PathNet or CoPath in the mid-90s. You might have updated somewhere along the way 10 or 15 years later. Jumped a version or two of HL7, and McKesson or ICE or Sunquest or one of those as an interface system. But it has not kept up with the DNA analysis and that technology. And the wonderful thing about standards is there's so many to choose from. Andy Tannenbaum, that's a great statement. One last point I want to make before we conclude. A lot of people claim that bioinformatics is really the rate limiting step, but we think about what information we want to extract, who decides what information gets filtered, is it ever appropriate to withhold information, what is our duty to reclassify or reinterpret information and recontact or report that to a clinic or a patient. This is information science. Maybe we should all be hiring like library people or something like that. It's not the traditional role of, again, like a med tech or bench tech or a clinician. A lot of great industries have solved these types of problems when it's not done as well in medicine. I think a conclusion or take-home message would be then bioinformatics expertise is certainly a necessary component, but really only one of the spokes of that wheel as you move through the entire process of orders, and sample comes in, sample prep, run the instrument, clean up the data, and report the data. It really requires several different slices of expertise, and it requires much more than the data analysis pipeline proper itself. To offer a clinical test and to do this nicely, you certainly need both parallel and strategic improvements in the test reporting environment and laboratory environment. So resources and strategy at a high level, hospital level or department level, in terms of interpretation and interface and implementation, I think are certainly key as we move forward into launching next generation sequencing in a clinical setting. And certainly like to acknowledge those in Utah, ARUP Laboratories and the Department of Pathology, Human Genetics, and the BMI department and high performance computing, and also my colleagues at Huntsman Cancer and Intermountain Health, and many, many academic and industry leaders that I've got to know quite well over the last 2 years. And with that, I'm happy to take some questions. Noah, please.
Thanks, great. Really nice talk. One of the things that we're in the midst of is building out our bioinformatics staff and infrastructure. And we have an existing bioinformatics staff that handles all of the things that one historically handles in a lab informatics infrastructure. So one of the real questions is, to what extent can a bioinformatics effort be integrated, or should it be integrated into sort of classical lab IT? And I'm wondering if you could say a few words about how ARUP approaches how much does staff cross over between areas, how much are they administered by the same group of people, those sorts of things.
So the question for the audience is how to deal with bioinformatics staffing, and where do they reside, who's in charge of them, where do you find that type of people, and what types of things do they do all day long. In an ideal world, you'd have a great king and he's in charge of everybody and everything, and he's nice and everything works smoothly, and one person's in charge. That's not always the case in an academic setting. We've had great success with a central core group of biostats and bioinformatics people, and embed them in the group where they do their work. We've had great success with that. We also like to keep a very clear, as a group, a very clear communication between a research effort, and as the development gets close to launching the test, that moves over more into a clinical or production environment. That line of communication needs to be very clear. Within that, what we've learned, I'll just mention this one last thing, it's very difficult to task the same person or the same group of people with development and pushing forward. You can't task that same group of people with the production day-to-day tasks. It's very, very difficult for the same person to cover all the day-to-day work and still stay up to speed on all the latest open source, whatever, the latest developments. And that really requires whether two different people or two different groups. And that's been successful in our area. Please.
Yes, you addressed the question of challenges of classification when everybody doesn't have access to complete data sets, and I think you mentioned the issues of public data sets versus private industrial data sets. How is that going to be solved, and what should society do to approach this question of having different data sets that may or may not be published and may not have peer review to make information available and make sure that we're giving the right information for patient care?
Yeah, so the question is how to leverage all the variants out there that are known, where are they, who to share them with, right, and how does that affect patient care, and what sources of information can you trust. So I think there's great efforts underway at a national level, recently funded, where 5 or 6 of the larger genetic testing laboratories will begin to share variants among and within each other, in the groups. Those will ultimately reside in NCBI's new collection named ClinVar. I think the latest numbers I've seen, that's up to about 42,000 something variants. Myriad Genetics is the only one that's opted not to share. There's a list of a couple, maybe 180 something laboratories that have agreed to share. This task is very difficult to do one location at a time. There's certainly a lot of advantage to everyone sharing with everybody else. My concern there is, I know this person over here does a great job, but these variants came from this person, and I don't really trust him, right? So again, it's a level of comfort. What they again try to do there is a staging area in between where the evidence counts have been announced, it hits a certain threshold, and it's released into the final release. So that intermediate or that staging area, as you assess evidence and how many times it's been seen in different locations. Some of these things are very rare, but that should not be an excuse for not trying and not sharing and putting the framework in place and moving forward with collecting those variants and sharing those variants. At the end of the day, whoever has access to the best collection of everything that's been seen makes the best interpretation. And that's simply, there's no other way around that. You think in terms of BRCA testing, no matter what the Supreme Court decision is, against Myriad or for Myriad, they still have a huge advantage because of all the testing that they've seen. So everybody might launch new assays, but in the interpretation piece, they have a huge advantage because of the collection that they've put together over the years. Over time, you would hope that so many institutions sharing to a central place, and the evidence is all counted up and scored, etc. Everyone has access to that. If you share it, you're able to see it. And I think it's a great model, and that's moving forward nicely.